Good morning, everybody. I'd like to thank the organizers for allowing every company to participate and to have a pre-discussion before the tender is being released. I think if every tender would be like that, that would be a lot easier for everybody. So I work for a company called Renishaw. We've been doing Raman spectrometer for over 20 years now. And I'm going to talk a little bit of what Raman spectroscopy is. Most of the consortium knows what it is, but I still come back into it. I'll explain what Renishaw instruments are at the moment and what we may do for this project. And finally, I'll go through some examples quickly. I think we fall in the tender requirements number 2, which, if I've noted correctly from Mia's presentation yesterday, the toolkit must allow further analysis of recovered trace. So from what I understand, the sample needs to be taken out from the toolkit to be analyzed on a Raman. So that would be correlation microscopy in effect. And I have to agree with the previous speaker, it's sometimes quite difficult to do, especially on a micron level. But it's certainly possible to do it, to localize a particle, to put it on another system, and to have it within the field of view of the objective, especially if you do things correctly, like keeping references and stuff. I'll explain what the type of system we can do. We offer to do these sort of things. So Raman spectroscopy, just a brief introduction. So it's a light matter interaction technique. It's been first reported by Raman in 1928. He had a Nobel Prize in 1931 for that. So basically, a laser light illuminates a sample. Most of the light is being scattered without change of energy. It's called Rayleigh scattering. It's elastic scattering. So it's with the same energy of the laser light. But tiny fraction, effectively a very tiny fraction of it, has undergone and is inelastically scattered. This is the Raman scattering. This change of energy is specific to the vibration of the molecule, and that gives really the information about the molecule, about the vibrational modes of the molecule. So the spectrum of the scattered light is then measured into a spectrometer and allows us to identify the sample and better understand its composition. So in the basic principle, how is a Raman microscope made of? Well, there are 3 main components. There's the laser, so monochromatic light source, a microscope, and a spectrometer. So the lasers, we can use multiple lasers, so going all the way from the deep UV to the infrared. I won't go through all the details of why you would use one laser or another, but in some cases you may want to use one laser, and in other cases another one. So it's always useful to have multiple lasers. You need a microscope to focus the light onto a very tiny spot. And also, with the microscope, you might want to couple that to a mapping stage to actually create imaging. The spectrometer itself is used to eliminate the laser light through some Rayleigh filters. Because the laser light being so much more intense than the Raman signal, you need to eliminate it to measure the Raman. And also it disperses the light onto a diffraction grating to generate a spectrum by measuring on a CCD detector. So what does a Raman spectrum look like? Well, I didn't take this example randomly. These 2 Raman signatures, one from amphetamine, which is a legal drug, obviously, against methamphetamine, which is illegal, as you probably all know. They are chemically very, very close to each other. There's only a CH group difference in the methamphetamine. Chemically, they are very, very close to each other. And I think there's going to be very little technique that are going to be able to differentiate it very easily. And as we can see with the Raman spectrum, they have 2 very different Raman signatures, and they could be easily identified one to another. So what kind of information can we extract from a Raman spectrum? Well, the characteristic frequencies, well, if we actually look at the Raman spectrum, we compare it to a Raman library, and we can actually identify one species or another. We can compare different spectrum to actually see whether one material is coming from the same place or is composed of the same thing, which is what we've done with the example before. We can look at the variation of intensity that can give you some semi-quantitative, effectively, information about the concentration of the sample. Looking at intensity variation can give you some crystallographic orientation information. The variation in bandwidth of the Raman band give you information about crystallinity, so whether you have a very crystalline sample, you have a very sharp peak, so if you have something very amorphous, you get something much broader. And the variation in band position gives you information about the stress, local stress on the sample. What are the advantages of Raman spectroscopy? Well, first of all, it's non-destructive and non-contact. So because we use an optical microscope, we're not in contact. And we're non-destructive in theory, unless you use too much power, and you just literally laser power and you burn your sample. But in theory, it's non-destructive. It's a flexible sampling, so you can actually measure liquids, solids. You have no sample preparation, and you can use an optical fiber probe to actually measure remotely. You have also a high spatial resolution, typically submicron. The negative point of Raman is, as explained below, this is quite a weak process because only a tiny fraction of light is has undergone a Raman effect. So you have quite a weak process. So it can be seen as quite slow as opposed to other techniques like fluorescence. So the different applications, I'll go quickly through that because to see the area of interest we are interested today. But one of the main applications at the moment is carbon. So any type of carbon, like graphene, obviously it's a monolayer of carbon, which is quite a hot topic at the moment. But also diamond, nanotubes, which used to be fashion as well. Characterization of photovoltaics, semiconductor, polymer science, material science, chemical industry, like the catalyst, which is quite big. Pharmaceuticals, which also going to interest us in a way in the forensics, because in the pharmaceuticals they actually do a mapping, a Raman mapping of a tablet, for example, for quality control. They want to have an even distribution of the active substances, and they can check that with Raman. I'll go through some examples about forensics, but Earth science, Bioraman for tissue imaging, and forensic science, which I'm going to go through in a minute. So the Raman, the Renishaw Raman portfolio. So we effectively have two systems. One which is more of a benchtop system, and another one which is the Raman microscope. So the Raman microscope, we call it the Via. I call it the Raman Swiss knife because it can do everything. Effectively. This is high performance. This is very flexible. You can just put as many lasers as you want. You have self-validation and verification. You can upgrade it if later on you realize you need another laser in the future. You can just upgrade it. It's fully class 1 if you want to. So you have an enclosure around the microscope on the left-hand side. And it's got dedicated forensics libraries. However, this remains an expert tool. So you need to know how to use it. This is, you need to know what you're looking for. So it can take a bit of time to actually grasp the use of it. We've got another type of system, which is our 800 series. So this one is really dedicated to one application. So there's no it's not configurable, so you actually choose the configuration when you start, when you buy it, effectively. So which laser you want, which objective, etc. So it's compact and robust. So this is a benchtop. It can sit on any table, effectively. This is non-expert. It's more of a push button. You still have some level of interaction with it, but it's a lot more user-friendly than the microscope. It's got self-validation and verification. It's fully class 1 as well. It's one laser, and it's dedicated, again, for one particular application. So how to use a Raman microscope? Well, effectively, here on the left-hand side, you've got the microscope part of the system. On the right-hand side, you've got a spectrometer. On the back, you've got the lasers. So you effectively interact between the microscope part on the left-hand side and the software. So effectively, you would load a sample onto your stage. You would focus it like any microscope, and you would take a measurement, and by setting up your experiment parameters, etc. So here on this picture, you've got a picture of the mapping stage, which is manufactured by us, by Renishaw. And I'm going to talk about it in a second, so to create images. So how do you create images? I think there should be a video here. No, the video doesn't want to work, but anyway, it moves normally. So when you actually create a Raman map, the stage moves under the microscope. So the sample moves under the objective, and you can recreate the spatial distribution of an entity. This stage has a repeatability of 100 nanometer. So it's not the resolution. The resolution is better than that. Actually, we usually specify the stages by the resolution, which is actually quite meaningless. The resolution is, you know whether plus or minus, if you have a resolution of 1 micron, you know within 1 micron where you are, but you're not necessarily 1 micron to where you want to be. That would be the repeatability. And here, we've got, effectively the resolution is the resolution of the positional encoders. While the repeatability is you are within here 100 nanometer of where you want to be. We've designed our own stage because actually no stage on the market was good enough for Raman spectroscopy. So that's why we designed our own stage. Again, this cannot cover an A4, especially with 100 nanometer repeatability, but it's got still 11 centimeter travel in X and 7 in Y, so that corresponds to, I think, the same as you, an A5 or something, A6 probably. So to cover an A4, you would have to split it in 4, effectively. And yeah, if you, I think if you have a correct reference mark on your tape or on your sample holder, I think it's reasonable. Depending of the repeatability of the stage of the toolkit, I think it's reasonable to have the sample within the field of view of the objective. So the sample of interest, when you take it from one system to another, to have it on the field of view of the objective. I think it's reasonable, but that means having a reference point on the sticky tape holder and an orientation. Obviously, that's something reasonable to think of. Also, in Raman mapping, the limitation we've had for many years is we were limited to flat samples because anything not flat would just lose the focus. So we've developed this live track technique. This is quite recent, actually. The video doesn't work again, but you could see actually the sample moving, and the Z positioning of the sample actually moves in real time. There's an automatic feedback to actually recreate, to actually have all the data on focus, so to keep the integrity of the data, and to have a good Raman data. Also, because we get the Z position of every point, we can recreate the topography of the sample. So this is a pharmaceutical tablet. So this is an overlay of the topography of the sample, of the white light image, and of a Raman map. So in false color here in cyan, you can see like the active ingredients of the pharmaceutical tablet. Also, is flexible sampling, so you can actually connect an optical fiber, so you can actually directly measure like further away in situ your sample. This is not a very good practice. You should be really wearing laser safety eyewear, but that's the way it works. Also, you can, if your sample is very large, like the A4 sample, you can use what we call a flexible arm, where you can actually deport the measurement while keeping the precise movement of the stage, because this arm is attached to the stage. So it's quite nice. You cannot, however, do mapping on A4 with such apparatus. So I go through a couple of examples. I'll go quickly because I think I'm running out of time. So the conventional explosive detection methods, well, there's a GRICE, which is quite old-fashioned, I guess, now. Nobody's using that. There's gas chromatography, which is obviously destructive. There's infrared. There's Raman spectroscopy. Raman spectroscopy has the advantage of being non-destructive, so it keeps the integrity of your evidence. And it can detect rather rapidly now different amounts of contraband substances. So there's one test which is actually quite standard use in aviation industry. Is one hand was in contact with Semtex and explosives, and it's been handled, and the thumbprint has been printed 40 times on different plates, and we've measured actually the 40th imprint. We've done a map of this fingerprint, which is, we have the white light image on the left-hand side, and we've got the Raman map on the right-hand side, and we could actually still detect the PETN, which is one of the substance of Semtex. I'm not an expert, but I guess you would confirm. So this is quite a sensitive technique in this respect. This is what we meant by this example. So question documents. So obviously the current technique is optical microscopy. Correct me if I'm wrong, but it can be sometimes quite tricky to actually. It's subject to interpretation, and depends of the user. Also, fluorescence spectroscopy, you need to have very different chemical substances between the two inks to differentiate them. Topographical methods is also quite tricky in the sense it depends the angle of attack of the pen, etc. And the SEM, it could be quite tricky to actually fit the paper and in the vacuum chamber. So on this example that we've done ourselves, this is the white light image of the crossed ink. Really, this is a reflected one without polarization, nothing. It's quite tricky to actually differentiate which one is on top of each other and whether they are the same ink or not. Well, with Raman spectroscopy, we can actually, the two inks have two different spectrum fingerprints, and we can actually easily differentiate them. And we can even see which one is on top of each other. So that's quite straightforward with that. So this type of map took, I think we've got the data here. No, I haven't taken it, but it takes about 12 minutes to actually take a map like that. And it contains about 12,000 points. So that's, although Raman is not a slow technique, you can still differentiate fairly quickly. But we don't see the scale here. We only like 400 micron. So you can imagine on an A4 piece of paper. So that's the two Raman spectrum of the two inks, which are very different to each other. So drugs also. So here there was an interesting case where we've measured a tablet which was still inside the evidence bag. So because the Raman microscope is intrinsically confocal, we can detect the Raman signal from the tablet with very limited contribution from the polymer of the evidence bag, which obviously is quite interesting for the forensics labs. So we could identify amyloid, the substance of interest on the tablet in a fairly straightforward way. So that's quite a useful tool for that. Same thing we've done from ecstasy tablet from the nightclub that was acquired legally, by the way. Just need to mention there's a fingerprint just to show like we can also detect the grease from the finger. So this map took. No, I think that's this one that took 12 minutes. That's not the one before. But this one contains 16,000 spectrum, and it took 12 minutes to obtain. So it's we now have some fast mapping functionality, which really helped in the last years for Raman mapping. So here we can even detect traces of cocaine within a fingerprint. So this is due to the high spatial resolution of Raman. And that's it for me. So if you have any question, well, that's the moment. I think it would be difficult for the Raman to be directly coupled to the toolkit. So I'm not sure if it's a requirement. At the moment, I don't think it is a requirement. But yeah, that's. Okay. Any question?
Maybe a comment. Actually, I'm a bit wondering why that people put so much effort in the scale of the A4. That's so difficult. We have in our lab, from a previous history, 15, 20 years ago, the fiber finder, and we bought it from a company. And within that system was a moving stage that is clearly bigger than A4. We lost all documentation in past years, so I'm not sure about the actual resolution. But I did some tests myself, and it's pretty okay. Within about 1 micrometer would do. The stage was meant for reflectance measurement, so it was completely black, which is not very good solid metal, so it's not very good for transmission measurements. But we cut a hole in it. I asked the technician to cut a hole in it. And it's now useful for transmission measurements as well. It was driven by a computer running Windows new technology, NT, which is not actually new technology anymore. But I asked a friend of mine, well, could you make some new processor for it? And he built an Arduino kind of thing on it. So I have now a thing up and running from an old machine, 20 years old almost. That is A4 and almost the correct resolution. I'm a bit wondering that people, that it's not available anymore. It doesn't seem available anymore.
There's two things here. There's the travel range, which is an A4, which is achievable. And there's the resolution or the repeatability of it. Obviously, if you want to have a 2-micron spatial resolution, you need to have at least a 2-micron repeatability. And to have such a good repeatability in such a long travel is actually difficult with this leverage. So, I mean, in our case, I mean, Renishaw is a metrology manufacturer, and we put a lot of effort to actually get 100 nanometer repeatability over 11 centimeter. So I can't even imagine how much effort there would be to actually get it in even longer distances. At least we've not done it. I'm not sure whether somebody else can do it, but I think it's tricky. And also, the stitching of the images, as Michael was saying, that there would just 14,000, as you measured this morning, you calculated this morning, 14,000 images, stick it together, is actually quite a lot, and it takes a lot of time, obviously.
Challenging. Yeah.
So it's not so much about the travel time, it's about the travel range, it's more about the specification of it, in terms of repeatability and resolution.
There's still a stage on the market, 30 by 30 centimeters, but it's exactly what you said, the precision at the ends is decreasing. Yep. So the values which are given by the producers are mainly dedicated for the middle, and the more you come to the random areas, the more the precision is lost. Therefore, we have the problem if we want to make coordinates somewhere, then the precision at the random areas is not good enough to find it back. If you think, for example, in spectroscopy we use 4 by 4 microns as a detection area, and the best quality of such a stage is 4 microns per step. So the precision, I think, is not good enough using such a large one. But you can buy them. You can buy even longer ones for the semiconductor business. But there are special ones. I think they are in the range of 20,000–30,000 euro per piece. And this will offer this. But the question is how much you like to pay for such a complete unit. because sooner or later we have also to talk this point, like Michael already discussed. In the semiconductor business, for example, they make instruments which are able to measure 190, all kind of autofluorescence, nanometer quality, but we talk about 1 million of investment per unit. And the question is, what is our goal to create an instrument? On the other side, okay, an electronic microscope also costs 1.5 million. You pay it once and you work for it for 10, 15 years. So let's say this is an internal political question.
The technology for the mapping stages is actually quite old-fashioned in a way. This is an infinite screw that actually drives the stage in and out, and there's a lot of frictions with such technology. And effectively, the fact that it's feedback controlled, you just keep on looking for the position. It goes left and right until it finds the position. But so that's why it's actually tricky to get 1 micron repeatability on a stage.
Yeah. Well, my opinion, I mean, on my point of view, I'm not sure if maybe I don't understand very well, but is it necessary to be exactly centered in the, I would say, the detected particles? Because if you are just coming back to the same field of view, I mean, in the camera field, that means if you have a 5 microns error or even 7 microns error, it's not really a problem because you can reposition the particles on the field of analysis of the spectro. So for me, the goal is, as you said, a 20 years old system is able to do that with such a repositioning faculty. So
as long as you can see it on the field of view, if you don't have to move around.
Yeah, but if you use 10x objectives, it's easy to get the field of view, and I think if you have a 5 microns error, I mean, you are still in the same field of view, so it's really easy because your particles is singular. I mean, the particles you detected is colored or is has a different shape, so it's easy to find it on a single field of view. So afterwards, you just have to click on it, then reposition and center it, and go to the spectral.
I mean, even if it's a 10 micron or 5 micron error, with the Timex objective, the spot size would probably be about 5 micron. So 5 micron would be acceptable, even without moving the sample, because the spot size would be just as big as 5 micron.
So that's why I'm not sure.
Even 5 micron is, I mean, I don't know, we have to do some tests, but 5 micron repositioning, whether if you don't move instruments, I think it's probably feasible. But if you move the sample from one instrument to another, 5 micron is...
I said 5, maybe, I don't know, what could be the limit. I mean, the limit is it's to be able to get it on the field of view of the camera. So
going from one system to another, there would be a mounting that needs to be very reproducible, which might mean expensive, because when you go from one to another, we've got some kinematic mounts with like a very repositioning, extremely precise, but that means that each sticky pad needs to be equipped, needs to be installed on such a mount, which probably adds up to the complexity of the system.
If you go to inter-instrument comparison, then micron is completely useless. Then I don't think it's necessary, because the first system indicates, well, there's an interesting trace on this position. You go to second one, and the second one will not be scanning. The second one will be just looking for a single trace, analyzing further. So if you have to select that one, it shouldn't be a problem. What I think is important is the bit within the shuttle toolkit. Doesn't really matter if you have a brute force approach or a first scan and a later more extended scan. But between those, I think you should be reproducible. If you have a brute force approach, then of course you measure everything at a single spot, you don't have a problem. If you scan the whole thing first and go back and do a more elaborate experiment on specific spots, you want to be sure that you analyze them on the correct spot.
I mean, if you can see,
So for that part, it would be important. And yeah, if the stage is not good enough and you can correct it in software, I don't mind, of course. But then you have to correct again, and if you don't have to correct,
is the fact that measuring Raman on sticky pads is actually quite difficult. It's quite difficult because we tend to use high laser power, and the from the experience I have on the sticky pads from SEM, is that actually we do burn the polymer underneath. Or if we don't burn it, the polymer being quite photosensitive or thermosensitive, I'm not sure which one, but it's actually retracting itself and we lose the focus. So we may consider transfer the fiber or whatever your sample is to another substrate, because
yeah, we put that specification, the Raman specification for within the tape, based on experience for drug laboratories that are nowadays portable instruments, and they can sense the contents through the packaging. So that's why we concluded, well, it should be possible to do that as well.
Through the packaging,
that's the basic of that specification. But if you get back that's not possible, then I mean, we should change it, or you should add up to it. Maybe
the technology of tape I've been using has evolved. I'm sure they have. They've been using standard like SEM ones, but this one tend to burn. And it's different whether it's on the packaging, because the packaging is above, it doesn't sustain the sample. But here, because the tape sustains the sample, and if it's retracting, it moves down, and we lose the focus, and we lose the Raman signal. That's the experience I have. Maybe like the new tape actually don't retract that easily. I don't know, but that would certainly something to consider. Would certainly be something to consider in the future. Or the alternative is to transfer the sample, but we know how difficult that is.
If that's needed, then that's needed.
Yeah.
Yeah.